Welcome, this is Jianying. I'm Associate Professor in the Faculty of Electrical Engineering, Mathematics, and Computer Science at Delft University of Technology. The topic of this lecture is motors and actuators in robotics. We will study what they are and how they work. We will start with the definitions of motors and actuators, then study their operation principles. After that, we will go through various motor types and actuator types. At the end of the lecture, we will have a preview of the motor to be studied in this course. So, what are motors and actuators? By answering this question, we will also see why they are important in robotics. By definition, an electric motor is a component that can realize power conversion from electrical power to mechanical power, that is to say, creating motion from electricity. In most cases, motors can also operate as generators, which can make the power conversion in the reverse direction, from mechanical power to electrical power. Actuator is a component which moves or controls a mechanism or system. Or in simple words, it's a mover which moves things. Usually, the movement of it is limited in range. The figure on the screen shows a linear actuator. You may see the bar in the middle would be able to be moved by energizing two coils on the sides because of magnetic attraction. According to how the move of the mechanism is realized, actuators can be categorized into electromagnetic actuator, hydraulic actuator, pneumatic actuator, etc. Generally speaking, an electromagnetic actuator is also a special type of electric motor, which only moves in a limited range. Now, we see electric motors and actuators are there to create motions, so they play important roles in robotics because they can convert electricity into motion. Now, let's move on to study their operation principles and types. It is useful to first review two important electromagnetic laws before we dive into various electric motor or actuators, since they all rely on electromagnetic principles. First one is the Lorentz force. It is governed by Lorentz law, which says the current carrying conductor will experience a force induced by the magnetic field B. In the rotational case, the force will create a torque. The force or torque will be the source of mechanical motion in motors or actuators. The other important law is the Faraday's law. When the conductor is moving inside the magnetic field B, the relative motion between the conductor and the magnetic field will induce an induced voltage inside the conductor. The induced voltage, together with the current flowing through the conductor, will create or consume electric power, depending on whether it is motoring or generating. These two laws tell us how mechanical motion and electrical power are related. Based on these two laws, we are able to make different types of motors. According to how the relative motion between the conductors and the magnetic field is realized and where the magnetic field is from, here we will see different ways to construct electric motors. The first one is based on the Lorentz force principle. The point magnets are stationary on a stator, and a constant current is passed through the rotor windings through a commutator, which produces a force on the rotor winding that rotates the rotor. The second one here operates based on the aligned torque between opposite magnetic poles, where both rotor and stator are equipped with magnetic poles, and hence the rotor rotates at the same speed as the stator magnetic poles rotate. This speed is defined as synchronous speed. The principle of the third one is called reluctance torque, where the torque is produced because the rotor iron poles tend to align to the magnetic flux lines, so that minimal magnetic reluctance is achieved. The rotor here also rotates at synchronous speed. The difference compared to the alignment torque is that the rotor poles are purely passive iron poles here. The final one is based on the induced current, where the rotating magnetic field from the stator induces a voltage and current in the rotor, and the interaction of induced current and the magnetic field produces torque in the motor. In order to have induced current, the rotor should rotate at asynchronous speed. That is to say, the rotor speed should be different from the synchronous speed. Based on above-mentioned principles, various types of electrical machines are constructed. DC motors operate based on the Lorentz force, synchronous motors rely on the alignment torque, synchronous reluctance motors rely on the reluctance torque, while induction motors are based on induced current. The last three types are called AC machines because they are fed by alternating or AC current. Here, you can see the actual cut view of 4 types of electrical motors that are discussed before. The top left one is the DC motor where electromagnet or permanent magnet poles are present on the stator. Direct current passes through the rotor through the commutator, producing the Lorentz force on the rotor. The top right one is the synchronous reluctance motor, where shaped iron sheets are used on the rotor to introduce different magnetic paths with different reluctances. The bottom left one is the synchronous motor, which has permanent magnet embedded on the rotor. This helps the rotor alignment with the rotating magnetic field and rotate at a synchronous speed. The bottom right one is the induction motor, where conductors are short-circuited on both sides and are used on the rotor to induce current. The 3 types of AC motors share the same stator structure, where 3-phase windings are used to create a rotating magnetic field. DC motors have brushes and the commutators, thus are less reliable and have less power density compared to AC machines, but will be the focus in the course because of its simplicity and easiness to control. Learning the DC motors and its control will help you build a solid foundation for more advanced AC motors. We now move on to electromagnetic actuators and see how they work and how they are categorized. In general, we can say electromagnetic actuators are electric motors that move in limited range. As you can see from the 2 animations on the screen, the one on the above shows the motion of a linear actuator, while the bottom one shows an electric motor rotating continuously. An electric actuator can be directly constructed based on Lorentz force. By placing a coil between 2 pairs of permanent magnets, as shown on the left, the magnetic field B generated by the permanent magnet will penetrate through the coil sides perpendicularly. When the coils carries a current I, there will be the Lorentz force exerted on each coil loop, given by the equation here. As we can see, the force is collinear with the current applied to the coil, which is a big advantage from the control perspective. However, this type of actuator has relatively low force density, which can be attributed to the large gap between magnetic poles. The large gap is needed to place the coil in between the poles. The second type of electric actuator is the reluctance actuator. The general structure of it is shown in the figure on the right. The stator consists of a magnetic core with a coil inside. The coil and the magnetic core then form an electromagnet. The electromagnet will attract the magnetic mover, just like a permanent magnet attracts the iron. Here, the equation for the attraction force is directly given without derivation. You may find a bit more detailed explanation and derivation in the read of this lecture. As we can see from this equation, the linearity is lost. Now, the force is a quadratic function of the coil current. This, of course, is a disadvantage from a control perspective, but the reluctance actuator has a higher force density than the Lorentz type, mainly because it needs a smaller gap to construct. The third type of electric actuator is a hybrid reluctance actuator. The structure of it is shown on the screen. The bar in the middle is a permanent magnet, while 2 coils with opposite direction of currents are placed on both sides. The force applied to the mover in the middle is then a combined effect of the permanent magnet and the 2 coils. In the end, if the current in both coils is with a magnitude I. The force applied to the mover would be the difference between the attraction forces from two sides. Again, the equation is provided without derivation. You may see that the hybrid reluctance actuator combines the advantage of both the Lorentz actuator and the reluctance actuator. It provides a linear relationship between the current and the force, also maintains a high force density. So, what type of motor we will study in this course? It will be a simple, low-cost but interesting one, the brushed permanent magnet DC motor. The hardware associated with this course is shown on the right of the screen. Throughout this course, we will focus on the servo motor module of the JAMS open source hardware, that is to say, the Diamond module of it. The Diamond module contains the motor drive printed circuit board, the brushed DC motor, and the 3D printed gearbox for speed reduction. All these resources are available on the GitHub page of the JAMS project, which you can find in the reader of this lecture. Hereby, we conclude the lecture. Thank you for watching this video. Good luck with the rest of the study.